And this morning we'll be looking at limit of functions like I explained to you the last time. And because of that, we'll briefly review we want to refresh our memories on some functions, some common functions that we saw previously in the very first lecture. Okay, so one of those functions was a cost function, which we plotted using Scilab. Okay, and we saw the domain that the value of one of f of x is always between -1 and 1 for a cos and a sine function. Okay, and when we plotted a curve, this is what we saw. So that is the behavior of the cos function. Then again, we have another function like the tan function. If you plot it, this is what we expect for the tangent factor. Then I ask you to read on some properties of trigonometry. So these are some basic rules on trigonometry, which I expect you to know. That is the sine squared of x plus the cos squared of x should be equal to 1. We call that the Pythagoras theorem. Then 1 plus tan squared of x should be equal to sec squared. 1 plus cos squared of x should be equal to cos squared. And then sine x plus y, standard as sine x, cos y plus cos x sine y. Whereas cos x plus y will be expanded as cos x cos y minus what? Sine y. And which means that tan x plus y will be expanded as tan x plus tan y over 1 minus tan x tan y. Okay, we also have inverse strict functions, okay, such as sine inverse of x. So when you see sine raised to negative, we call it a sine inverse or the arc sine. We also have the cos inverse of x, which is arc cosine. We have the tan inverse, which is the arc tangent. We have the cosec inverse, which is the arc cosecant, and then we have the sec inverse, which is what? Arc secant. Same with the cotangent, arc cotangent, which is cot inverse. Okay, then again we have what we call as the hyperbolic functions. Okay, so this is how they look. For hyperbolic functions, we have so sine it's like sine, but you see you have the hyper here. So sine x is defined as half of e raised to the power x minus e raised to the power -x. And then cos x is defined as half times e raised to the power x plus e raised to the power -x. And the rest follows, okay, suit. So if you want tan s, it's just sine s over cos, okay? We know tan is always cos, sine over what? Cos, So it follows you to develop the various what? Hyperbolic functions. Now, moving on, we have already looked at all of this. Now, today we are looking at the concept of limits and finding the limits. Then we will be looking at the concept of one-sided limits, infinite limits. And if time permits us, we'll look at the concept of, okay, good. Now, for some of you in class, I introduce you to the concept of limit, others not. So we'll begin from the very scratch. When we talk about the limits, then we say that a limit is defined as The limit of f of x, this is how it's read. The limit of f of x as x approaches a is equals to L. Okay, so, and this is what it basically means. Let's say we have a function. We are looking at the behavior of the function. Okay, so, and let's say we have f of x here. So here we have f at x plus h, or let's say f at x, sorry, f at x. Then this is x here. Then we have the value, say, f, where the mistakes? Okay, so we have the value, say, a. Okay, so let me get something like that. Let me have another value, say, x plus epsilon. Okay. Okay, then we have f at x plus epsilon. Okay, so what do we mean by the limit of f of x? This is the function. The function is the curve. Okay. Now, when we talk about the limit of the function, then we mean the behavior of the curve. As we approach a certain point A on the x-axis. Okay. That is why we have x approaching A. Okay. Written down. So as x approaches a certain point A, we want to investigate the behavior of the function. So what is the nature, or where is the function headed when we are heading to A? So you see that the value of the function, let me change the marker. The value of the function seems to be rising and rising and rising till we get to a certain value. When you find the value of the function, it is a certain value L. It appears to be hitting the value L. So we say that the behavior of the function, okay, of f of x, as we approach the point, as x approaches the point A, okay, is equal to what? Is equals to a certain value L, meaning the value of the function at the point A appears to be equal to L. The same way, if we were coming from the right hand, this time we're going from the left hand, left to right. Now, if we were coming from right to left, okay, let's examine the behavior of the function. It is going down, decreasing to the same point. It appears to be hitting the same point, which is what? The same value of L. So because we are approaching L, when we come from both the left hand and the right hand, okay, we can say that then the limit of this function, the behavior of the function as we approach A, L, okay? So what you see as a limit of f of x as x approaches A is just the behavior of the function as it approaches A, okay? Good. So this is the meaning of what you have up here. Okay. Now, because we are saying that it is the behavior of the function and not the value of the function itself. Okay, sometimes the value of the function may not exist. Like in this graph here, I have an open space here. It means that there is no value of the function. The function is broken at the point A. But here we are talking about behavior. How does a function behave when we are approaching A? We are not saying that what is the value of the function point A. We're only saying how does it behave? And clearly we can see that as we are approaching A from the left, the function is behaving like we are getting to L. The same way as we are approaching A from the right, the function is decreasing towards what? L. So we can say that the limit exists and is equal to L. Okay. Then again, there is something we need to understand, that anytime we talk about limits, we talk about the, as x keeps going, because we will never get to the point A, we always say x is approaching A, right? So we get close enough to the point A with a certain neighborhood or a certain space around A, and that space is referred to as epsilon. Okay, there is always a space around A, a neighborhood around A, which we call as what? Epsilon. Okay, so we'll look at that when we get to the actual definition, the mathematical definition of the limit. Okay, so let's clear this for now. Now, having explained the concept of it as the behavior of a function, okay, we say that indicates the value L of the function as x approaches the value A. It is employed particularly in situations when the value of the function itself does not exist, okay? Even though the value of the function does not exist, we can examine the behavior. Oh, the function appears or is behaving to hit that particular value, okay? Even though at the point A, the value of the function will not exist. Okay, so moving on. Yeah, so now I'm going to save this one. I think I've hit on that point where we can evaluate the function from the left or from the right, okay? Good. The next thing we want to look at is the concept of the uniqueness of the limit, okay? We say that the limits of a function should be unique in the sense that if the limit of a function is approaching, say, a value L, and for the same function, you evaluate the limit and then it is equals to a certain value N, then we are saying that we cannot have two value limits, which means that L must be equal to what? M. In other words, the limit of a function should always be one. It should be unique. It should be a singular value. You cannot have two limits, two values of the limit for the same thing. If you have two values, then it means that the limit does not exist. It has to be what? Unique, as long as the limit what exists. So you take note of that. Now, the first example we want to look at is how to evaluate the limits. Okay, good. And it is just like finding the value for polynomial functions. If you want the limit, you just substitute the value of A into the given function. So if you are given, for example, to find the limit of, we are to find the limit of x squared plus 2 plus 4 as x approaches 2. All you are going to do is substitute the value into the function. That will be 2 squared plus 2 times what? Times 2 plus what? Plus 4. So 2 squared will be equal to 4. Then 2 times 2 is also equal to 4. Then plus another 4 will give us 4 plus 4 plus 4 will be equal to what? Will be equal to 12. Okay. So for a polynomial function like we have, the limit is just obtained by substituting what? The value A, okay, into the function. Okay. Now, We want to look at some rules on the function, on limit itself. The first thing we have to notice, if the functions f and g are functions such that the limit of f of x as x approaches a certain value c exists and is equal to a, and the limit of g of s as x approaches the same value exists and is equal to b, then the limit of the summation of the two functions is going to be equal to the limit of the first function plus the limit of the second function. Okay, so that will give us the limit of f of x plus the limit of g of x, okay, which will be equal to, but we know that f of x is a per this formula here, and the limit of g of x is b per the formula here, so that will give us a plus b. Then the next rule, we are saying that when you have the limit of a certain constant, okay, times f of x, so if you have a constant, maybe 2 times limit of 2 times f of x, a given function, as x approaches c, then this can be found as 2 times the limit, okay, of f of x as x, so meaning you bring out your 2 as x approaches the value c, okay, and because the limit of f of x as x approaches is equal to a, we can say it's equal to 2a. Okay, the same way, if we are finding the limit of the product of two functions, then it's going to be the limit of the first function as x approaches c times the limit of the second function x approaches c, okay? And we know that the limit of the first function is what? Of f of x as x approaches a, c is a. And the limit of the second function is also b. So we have a times what? Times. So I want you to write down the rules briefly, then we continue. I'm giving you some few minutes, let's say 1 minute to write that down. Yeah, I believe you are done with the rules. Let's continue. Good. Okay. So we want to take some few examples, okay, on the limits based on the given rules. And then we want to see, in fact, try to understand how to evaluate the limits. So let's say we have questions like f of x is equal to 3x squared, okay, minus 2x plus 1. And I ask you to find the limit, okay, of f of x as x approaches, say, 2. Okay, good. So because this is a polynomial function, in our solution, all we'll do is to substitute the value of 2 into the function, okay? And then simplify it to get our limits, L. So this will be 3 times 2 raised to the power 2 minus 2 times 2 plus 1. Okay, this will give us 3 times 4, which will be 12 minus 4 plus 1. So 12 minus 4 is 8 plus 1 should give us 9. So the limit of the function is equal to 9. Okay, what next? Let's try another one. So we want to try, we have f of x equals to 2x plus 1. Then we have g of x equals to, let's say, 5x squared minus 1. And I ask you to find the limits. We have to find the limits lim of 2x, or let me say f of x times, okay, g of x as x approaches the value 0. Okay, there are the rules. This can be redefined as well. Lim of what? Lim of the first function, it will be 2x plus 1 as x approaches 0 times the limit of what? The second function, which is 5x squared minus 1 as x approaches what? 0. Okay. And since they are both linear, I mean, functions, we substitute into the function. This should give us 2 times 0 plus, okay, that is for this function here. So we'll put in brackets times what? The we'll put another bracket. That will be 5 times 0, okay, squared minus 1. So 2 times 0 plus 1 will be 1 times 5 times 0 squared will be 0 times minus 1 will be -1. So when we multiply, each of the function will equal to -1. Okay. So these are two first examples which we've considered in class. Let me take your questions if there is any.
Hello, sir. Please, I can't see what you are sharing.
I don't know how to.
Okay.
Yeah. Any other question? Okay. We have more examples here to try. So try the first one for me. Find the limit of 2x plus 1 as x 2 for me. So what value did you get? Yeah, favor. Favor, what did you get?
5.
5, you are correct. So the answer is 5. Now, this will be limit. So this will be limit. When we are finding the limit, we said you just substitute because of polynomial function. Okay. So this will be 2 times 2 plus 1, which is 4 plus 1, which is equals to what? 5. Okay. Very good. So in the next example, we're going to first of all add another rule. Okay. So add this rule to your rules you have there. So that will be rule 4, which is the limit of f of x over x means a rational function as x approaches the point C will be equal to the limit of f of x as x approaches C over the limit of g of x as x approaches C. I hope you are writing. Okay. Then let's add this one. So rule 5 will be the limit f of x raised to the power, let's say 1 over n, the nth root, as x approaches C will be equal to the limits the limit of the function f of x as x approaches C, all raised to the power the index. Okay, so assuming the limit here is a, this will be a raised to the power 1 over x. Okay, so make sure you have these rules down before we continue. Yeah, I'm sure you are done by now. We want to continue with the next example. Now, when it comes to rational functions, okay, most of the times they are given the limits. Okay, some values of x make the function, okay, become an indeterminate form. What we mean by indeterminate form is having 0 divided by 0. Okay, we call it indeterminate form. So we want to avoid this scenario. We do not want to be seeing 0 over 0, okay, in our evaluation of the limits. Okay, so anytime we have 0 over 0, we'll try to find means at which to further reduce the given question. Okay, so let's try this first example and see if we'll get an indeterminate form. So for this first question, per the rules, we are going to get the limit of what? The numerator function, which is x squared minus 9 as x approaches 3 over the limit of what? X plus 1 as x approaches what? 3. Now let's see the results we'll get. So in the upper limit, we have 3 squared minus 9. And then here, down here, we are going to get 3 plus 1. So let's do a little bit of investigation. 3 squared minus 9 will be 0. This is 0. But the denominator is not 0. The denominator is 4, right? So we don't have any problems. So that should give us a value of what? 0. 0 over 4 is equal to what? 0. So 0 is a number, but 0 over 0 is an indeterminate form. 0 over 0 is an indeterminate form. So let's take another example. Assuming for the same question, I'll change the denominator to look like this. X squared minus 9 over x minus 3. X minus 3. Okay, and I ask you to find the limit as x approaches what? 3. Then per the evaluation, I'm going to skip this step. So let's go straight to the next step. This will be 3 squared minus 9 over 3 minus 3, right? Clearly, we can see that 9 minus 9 will give us 0. Okay. Then 3 minus 3 will also give us 0. Now 0 minus 0 is an indeterminate number. Okay, or an indeterminate form, and we do not want to see that. Right? Because of that, we will have to find a way to reduce the original question that was given. Okay, now let's see if that is possible, if we can reduce the original function. Now, indeed, that can be done. When we look at the numerator x squared is a square, minus 9 is also the square of 3. So this is a difference of 2 squares, okay? So the numerator is x squared minus 3 squared, which is the difference of 2 squares, okay? And the denominator will be a factor of those multiples. So this is how the question can be reframed. Limit of x as x approaches 3, okay? And because it's a difference of 2 squared, we can write the numerator as x minus 3 times x plus 3. Okay, all over the denominator, which is x minus 3. Okay. That is the case. Let's bring the limit. So this is lim as x approaches what? 3. If that is the case, then we have x minus 3 here, which can also cancel out the denominator, which is x minus 3. Okay, so it means that the question is reduced to limit of x plus 3, okay, as x approaches 3. And that is simply going to be equal to 3 plus 3, which is equal to what? Which is equal to 6, okay, which is a real number. Okay, if you have any questions, you can ask before I move to the next page. So we have another example on the board. We have to find the limit of x squared minus 4 over x plus 2 as x approaches minus 2. And clearly, once again, we can see we have a difference of 2 square scenario. Okay, and that can be, this is x squared minus 2 squared. So that should give you, when we re-express it, that will be x plus 2 times minus 2. Okay, so if that is the case, then it means x plus 2 will cancel out the denominator, which leaves us with x minus 2 in the numerator. Okay, so once we evaluate the limits, that will give us negative 2 minus negative 2, which will be equal to minus 4. Okay, instead of, if we had tried evaluating the limits right from the beginning, that would have given us an indeterminate form. So if you have put negative 2 squared here, negative 2 squared will give you 4. 4 minus 4 means numerator will be 0. And then negative 2 plus 2 will also be 0. So that will be 0 over 0, which is indeterminate. Okay. Hence the need to re-express this using what? A difference of 2 squares. And then reducing the expression to get what? Negative 4 for our answer. Okay. Now, moving further, we want to try rule 5. Okay, the one with the power rule. So for rule 5, we're told that to solve it, you have to just bring the power out. That will be everything raised to the power, the root, which is raised to the power half. Then that will be limit of what? The function, which is s squared plus 5. Okay, as x approaches 2. So this should give us, when we evaluate the limit in the bracket, that should be 4. 2 squared is 4 plus 5 raised to the power half. That will be 9 raised to the power half, which is equal to what? 3. So that is our limit of the function. Okay. So piecewise function as f of x equals to 2x squared plus 1. Okay, and then x plus 2. Okay, you remember the robot scenario when we're doing functions. So we have it again, and let's say the function is this: when x is greater than or equal to 1, and then the function is this value when x is less than 1. So what do we mean? What we mean is, like we saw from our graphs in class, okay, that at the point, say 1, okay, when x is greater than 1, for the first domain here, x greater than 1 means the values of x on the right hand, okay, good. And we know how this function looks like. S squared always looks like a curve. Good. And since it is s squared plus 1, the function will look like that. And again, x is part of the domain. So when we are shading it, it will look like a function like this. Okay. It will look like this. Okay, for x values greater than 1. We've seen this curve, the curve of s squared in class. And I told you, be experimenting more with Scilab. Okay, good. Then for the linear function, which is x plus 1, when x is less than 2, okay, that is also going to be, if this was at 1, this would be at around 2. Okay, when x is less than 2, this is going to be open here at the point 2. Let's find the value of f of x at the point 1. So f of x at the point 1 will be, if x equals to 1, then for this function here, this will be 2 times 1 plus 1. So that will be 3. Okay, so which means the value here is 3. Okay, whereas for this function, when we find when x is equals to 1, 1 means 1 plus 1, which is also equal to what? 1 plus 2, which is also equal to 3, right? So that function will also be plotted here. But we take note that x is not part of the domain for this particular function, okay? So it's going to be plotted, it's a linear function. So it will go as a straight line like this, okay, with the intercept of 2 over here. Now, what do we mean? This simply means that when we are approaching x, you remember we said the limit of the function is the behavior of the function as we approach a point, okay? Now, if we are approaching this function from the left hand, to the point x equals to 1, we see that the function is going up, is increasing. Let me change my marker so that you see clearly. So whilst we are approaching x, this is the nature of the function. It keeps going up, keeps going up, keeps going up, and it appears to be hitting the value what? Y equals what? 3. Okay. So when we are going, we are reaching the, or we are approaching the value 1 from the left. This is how we write it. We say the limit of the function f of x, okay, as x is approaching 1 from the left, you put a negative there. Okay, take note, this negative is not -1. It means x is approaching 1 from the left hand. Okay, that is how it is written. Then, as we can see, the value there is equal to 3. When we are approaching from the left hand, the limit, the behavior is equal to 3. What of from the right hand? So I'll use another marker. So on the right hand, let me use say green. When we are approaching 1 from the right hand, okay, you can see that the curve is decreasing, decreasing, decreasing. Then it will rise a little bit, and then it rose, and it appears to also be hitting the value of 3. So that too, we are going to write that the limit of f of x as x is approaching 1 from the right hand. So you say positive is also equal to 3. So the behavior of the function as we are getting to 1 is the value of f3. Good. Now, in this scenario, we can clearly see that the limit of the function as we are approaching from the left hand is equal to the limit of the function as we are approaching from the right hand. And anytime we have such a scenario where the limit, just a moment, where the limit of the function of f of x as we approach a point, say A from the right, from the left hand, becoming equal to the limit of the function as we approach A from the right. So xs approaches A from the right hand. We say that then the limit exists. It means that the limit will exist and is equal to a certain value, say L. Okay, so in this case, we have limit of f of x as s approaches the value A is equal to limit of f of s as s approaches the value A plus is equals to 3 in value. Okay. Very good. So that is what the rule seems to demonstrate. So clearly, I'm going to go back to the rule so that we try to just follow once we understand what it means. Okay, sorry. Yeah, so we are saying that for 100 one-sided limit, okay, we are saying that the limit of f of x as x approaches c from the left. So when you see a negative, we say from the left is equal to a certain value k, and call k the limit from the left or left hand limit if f of s is close to k whenever x is close to c, but to the left of c on the real number line. Then this is also called the limit of f of x from the right hand, okay? If f of x is close to L whenever x is close to C, but to the right of C on the real number line. So anytime the limits from, so we are saying that in order for a limit to exist, the limit from the left hand and the limit from the right hand must exist and be equal. Okay, the limit from the left hand must exist. So in our example, we saw that the limit was equal to 3. And the limit from the right hand must also exist. And we also saw it was equal to 3. And they must also be equal. So once they exist and they are equal, then we can say that then the limit of the function exists. Okay, so let's take some further examples and give this a try. So I'm going to take a function like f of x is equal to 1 minus 2x squared. Then I have 2 minus 3x as x is less than or equal to 0, and then x is greater than 0. Now I'm asking you to find the limit of f of x as what? As x approaches the value 0. Okay, so what do we do? First, you have to find the limit. The first step, you have to find the limit of the function from the left hand. So we're going to write first limit of f of x as x approaches 0 from the left hand, okay? So this is our solution. So when we are approaching 0 from the left hand, is a function. This is the value 0. And we are saying we are approaching x from the left hand, okay? If we are approaching x from the left hand, then we are talking about what? Values less than what? The values of x less than 0, okay? Because from the left hand, you have -1 there. You have -2, you have -3, and so on and so forth. So we are talking about values less than 0. So if that is the case, then we are looking at this domain where we are less than or equal to 0. If we are on this domain, then it means that the value of the function is what we have here, okay, per what we know from class. So which means that this will be the limit of what? 1 minus 2x squared, okay, as x is approaching 0 from the left. And this will be, you see, it's a polynomial function, so we'll just evaluate. The trick here is identifying what domain is needed. Once you find a domain that is needed, select the function on that domain. So it's just like I explained to you in class. Once a robot is moving and in the absence of an obstacle, it may be using a particular function. But once it detects an obstacle, it switches to another function, meaning the domain will change. So the function will also change. That is exactly the scenario we have here. So we have 0 from the left hand. The value is 0, but just that we are approaching from the left. So when we substitute, that will be 1 minus 2 times 0 raised to the power 2, which is equals to what? 1. Okay. Then what's next? We'll go and find the limits from the right also. So the limits of f of x as we approach x from, as we approach 0 from the right hand is going to be, now when we are approaching 0 from the right hand, this is the right side. We are approaching 0 from the right hand. So on the right hand of 0, we have positive values, which is s equals to 1, 2, 3, and so on and so forth, which means that those values will be greater than what? 0. Okay. So if greater than 0, then we are on this domain, right? So which means that the function corresponding to that domain is what? 2 minus 3x. So we are dealing with the function 2 minus 3x, okay? As x approaches what? Approaches 0 from the right hand. So when we do this substitution, this should give us 2 minus, we are just going to put in 0 because it's a linear function. So 3 minus what? 3 times 0. And this is equals to what? 2. Okay. So when we look at the rule, we can see that the limits exist. The first limit is 1. The second limit is 2. But are they equal? No, they are not equal. So we are going to write, since, okay, since the limits, Elikem, you are writing on my screen, since the limit of f of x, okay, from as x approaches 0 from the left is not equal to the limits as f of x approaches 0, the limit of f of x, sorry, as x approaches 0 from the right, okay, you indicate that the limit does not, you write, does not exist. So DNE means does not exist. So since the limit from the left hand is not equal to the limit from the right hand, then the limit, okay, you write then, okay, lim of f of x, okay, for the lack of space. So let me clean that side. So this is right, that since the limit of f of x as s approaches 0 from the left is not equal to the limit of f of x as x approaches 0 from the right, comma, the limit of f of x as x approaches 0 does not exist. Okay. Yeah, so if you've examined it carefully, you can raise your hands for questions if there is any. Yeah, so we have Paul Adakwa.
Sorry, it was a mistake.
Okay.
Yes, sir.
If there's any question you can ask, but if it's clear, then we move on. Yes, I was hoping that you will not ask questions, but you still have questions to ask. Yes, Isaac. Isaac, unmute yourself and speak.
Sir, please, will it be the situation when a question is given and you did not try to put it on a graph? Can you go straight and solve it by how you did, and then you demonstrate the graph?
Yes, I don't need a graph. I only need you to solve, but for the sake of explanation, I indicated a graph. So for the limit of the function, the rational function, x squared plus x plus 2 over x squared minus 2x minus 3 as x approaches 3. And like I said earlier, once we are approaching 3, the value 3 from the left, then possible values will be 0, 1, 2, all the way to 2.99 something before we hit 3. Okay, so we are finding limit from the left first. This will be x squared minus what? 2x minus 3. Now, this, if we evaluate, should give us what? Let's say we have a value around 2.9. Okay, we just want to do some investigation. So have your calculators by you. 2.999 plus, okay, 2.99 plus 2 over 2.99 squared minus 2 times 2.99, okay, minus 3. Do the calculation for me. So if you got a value, just type it in the chat page for me. So here is 139 something, 392 point something. Good. Now, if this value gets increasingly big, very close to 3, let's assume we put 3 into this function. This will be 3 squared plus 3 plus 2 over what? 3 squared minus 2 times 3. Okay, minus 3. So the numerator so the numerator will be what? Will be 9 plus 6 plus 2 over 9 minus 6 minus 9. Okay, now my 9 minus 6 minus 3, 9 minus 6 minus 3 is 0, and the numerator is going to be 17. 17 over 0 is going to be infinity. Okay, don't forget infinity is a number, so it will be infinity. But what kind of infinity? We can clearly see that when we were approaching 3, let's say this was the value 3. When we were at 2.999 at 2.99, positive 2.99. The value we're getting was negative, negative. So it means that we're actually getting a negative infinity. If we were going to evaluate the limits from the left hand, okay, we'll get a negative infinity. Now, what if we were working from the right hand? So on the right hand, let's say this is 3. Whilst we were coming, we have bigger values like 3.9, okay, 4, and so on and so forth. So if we are fix our value of say 3.01, okay, because that will be a value before we come here. Then the limit from the right hand of x as we approach 3 from the right hand will be what? 3. We are just selecting a value of 3.01. So 3.01, please, all questions must hold on. 3.01 squared plus 3.01 plus 2 over 3.01 squared minus 2 times 3.01 minus 3. Okay, so I'll need your answers from the chat page. I don't know, but I think I'm muted along the line. So let me do this again. The limit as you obtained was positive 350.876. And we are saying that if we were to put it exactly 3, then we'll get a positive infinity, okay? That suggests to us that the limit on the left, which is negative infinity, is not equal to the limit on the right, which is positive infinity, okay? So we conclude by saying that the limit f of x as x approaches 3 from the left is not equal to the limit of f of x as x approaches 3 from the right. Hence, the limit of f of x as x approaches 3 does not exist. Okay. So we're next going to look at limits as x approaches infinity, which is usually written as the limit of a function, say f of x, okay, as x approaches infinity, either positive infinity or negative infinity. We want to look at the behavior as we approach positive or negative infinity. Good. Now, the rule there too is, in most scenarios, as long as we have a rational function, it is likely we may end up getting infinity over infinity, okay, which is another indeterminate form we do not want to see. So infinity over infinity is also an indeterminate form which we do not want to see, okay. Then sometimes too we can have 0 times infinity, okay. when we have a multiplication scenario, we don't want to also see 0 times what? Infinity. So these are some of the key things, indeterminate forms we do not like to see. Good. So you keep that at the back of your mind whilst we solve limits as x approaches infinity. Good. So to start it off, we'll go back to a question we skipped in the slide, which is of that form, okay? And then we solve that question. Okay. Yeah, so we have to find the limits of t squared plus 5t minus 9 over t 2t raised to the power 4 times t 3t cubed, okay? And we have to find the limits as t approaches negative infinity, okay? This is it. T approaches minus infinity. Okay. So what do we do? First, we need to do some investigation. If we are finding the limits as t approaches infinity, then it means that if we put, let me clean this first. We want to just do an investigation. If we substitute directly, because they are all polynomial functions, if we make this infinity square minus 5 times minus infinity minus 9 over 2 times infinity negative infinity raised to the power 4, okay, plus 3 times minus infinity raised to the power 3. Now, infinity plus any number is infinity, and infinity times any number is infinity, and the square root of infinity or any power of infinity will still give us infinity. So which means that infinity squared is still infinity, okay? Then minus 5 times infinity is still infinity. Minus 9 is still infinity. So the numerator will actually be equal to infinity. You understand? But let me write it in the next step. Then again, the denominator will also be infinity, because 2 times infinity will still give you infinity, plus 3 times infinity is also infinity. Infinity cube is infinity. So numerator and denominator are both going to be infinity over infinity. Here we are not very much interested in the signs of the infinity, because infinity over infinity or negative infinity over negative infinity are still indeterminate. So evaluating directly will give us an indeterminate form. So then what do we do? The rule is anytime we get indeterminate form, you are supposed to change what the expression. It's a must. You have to change the expression to get a much simpler expression. How do we do that? It's quite simple. Now, what we'll do is, you are first, please just give me a minute. To simplify into another form, we'll divide all the terms in the denominator and the terms in the numerator by the highest coefficient, okay, in the denominator. Good. And I like the way it's been done here. You see, it's quite simple. What it says is you're going to, I'm seeing factorization and division, but an easier approach to that, per the class that I know, okay, what you can do is just divide through by the highest factor of t. So we have 3t cubed. Okay, numerator 2 is what? T squared. T squared minus 5t minus 9. So the highest degree of the polynomial is what? T raised to the power 4 here, right? So let's divide all terms by t raised to the power that degree. So we divide here by t raised to the power 4, divide this by t raised to the power 4. Do same for all the terms in the numerator. So t raised to the power 4, okay, then divide this by t raised to the power 4, and then do same for this, which will be t raised to the power 4. Okay, once we do that, this will give us t squared will go into t raised to the power 4, t raised to the power 2. Okay, minus t goes here, t cubed. So we have 5 over t cubed minus, we have 9 over what? T raised to the power 4 all over t raised to the power 4 will cancel out this. So we are left with 2 plus t cubed goes here, t times. So that will be 3 over what? Over t. Now this looks much a simpler expression. Okay, good. Now, the reason why we are confident in this is we know that 1 over infinity is also equal to what? Is equal to 0. Okay, so if we put infinity here, this term will go to 0. If we put infinity here, this will go to 0. If we put infinity here, this will go to 0. So the numerator will be 0. And then if we put infinity here, any number divided by infinity will give us 0. So if we put infinity here, this will also go to 0. So we know the denominator will be 2. So we'll get 0 over 2, which is not an indeterminate form. Okay, so now we are confident that this reduced form will give us the answer. So which means that the original question is going to be reduced as this. So then we write this equals to the original question equals to the limit as t approaches what? Approaches negative infinity. Okay, and this will give us, when we put it in there, this will be negative infinity squared minus 5 over minus infinity cube minus 9 over minus infinity raised to the power 4 all over, we have 2 plus 3 over minus infinity. Okay, good. So when we go here, 1 divided by infinity squared will be 0. So that will be 0. 5 divided by infinity cube will also be 0. Okay, there's nothing like plus 0 or minus 0, so 0. 9 divided by infinity is also 0. Then in our denominator, 2 plus 3 divided by infinity is also what? 0. So the final answer is going to be 0 divided by what? 2. And 0 divided by 0 is equal to the answer 0. So hence, the limit of the function is equal to 0. Okay. So if you have any questions, quickly ask, like I said. We'll take one more example. So that will be, we are finding the limit of 3x squared minus, no, plus 7x minus 6, which is on page 67 of your textbook. So over 4x squared plus 3x plus 6. And we have to find the limits as x approaches infinity. Okay, so the first thing is numerator is what? Polynomial. Denominator is also polynomial, which means we will just evaluate straight away, right? But we need to do an investigation to find out if we get an indeterminate form. If we substitute infinity into numerator, we'll get infinity. This will be 3 times infinity squared plus what? Plus what? 7 times what? Infinity minus what? 6. Okay, over 4 times infinity squared plus 3 times infinity plus what? Plus 6. So numerator will be infinity over what? Denominator will also be infinity. So which means we need to what? Re-express the rational function here. Okay, so let's do that. So if we re-express, we are going to get, we'll use the same principle we just made use of for. We divide through by the highest factor, which is x squared, right? So in the numerator, we'll have x squared divided by x squared, 3x squared divided by x squared, plus 7x over what? X squared. Then we have minus 6 over x squared all over 4x squared over x squared plus what? 3x over x squared plus 6 over x squared. Okay, so once we've done that, this will cancel out. So we get 3 minus 7 over, sorry, plus 7 over what? Over x minus 6 over x squared all over what? 4 plus 3 over x, okay, plus 6 over x squared. Okay, then now we can evaluate the limits. Okay, don't forget to bring the limit whilst simplify. So this limit as x approaches what? Infinity. And same here, lim, okay, as x approaches infinity. Okay, so now we'll evaluate the limit. That should give us 3 plus 7 over infinity, which is 0. Minus 6 over infinity is also what? 0. Then we have 4 plus 3 over infinity, which is 0. And then plus 6 over infinity, which is also what? 0. So the final answer is going to be 3 over 4. So final result is what? 3/4. Okay. Yeah, so now if you have any question, you can raise up your hand and ask so that I can address for you. So, like I said, we want to look at L'Hopital's rule, okay? The L'Hopital's rule, which helps us to also deal with indeterminate what? Forms of function, okay? So L'Hopital rule. Now, what does the L'Hopital rule say? The L'Hopital rule says that if you have a function f of x over g of x, and we have to find the limits, okay? Once you do a prior investigation, as x, let's say x approaches, okay, any value, say a, any value, say a, and you realize that we are going to end up getting an indeterminate form, 0/0. Okay, then what you can do is you just have to differentiate the function. Okay, so you differentiate the function and find the limit of the derivative. So you find derivative of f, and then you find the derivative of g. Okay, and then find the limits. That will help us to go around what? The indeterminate form. So a very basic example will be, now the challenge here will be how to find the derivative, okay? The rule for the derivative is as follows. If I give you a function, say f of x is equals to say 2x squared or x cubed, and I ask you to differentiate this with respect to x, okay? Then what you do is, let me rewrite this for clarity. So if I ask you to find the f of x, that's differentiate the function with respect to x, then what you do is you bring the power to come and multiply. So you have 3x, then subtract 1 from the existing what? Power, okay? You subtract 1 from the existing power. So we have the power there was 3, we'll subtract 1 from it, that should give us 2. So this gives us the derivative, okay? So that is how you differentiate what? A polynomial, okay? Good. So with this rule, we are going to try the first example. So let me keep differentiation on the board. And let's try one example. So assuming I give you a function like limit, we have to find the limit of, say, x squared plus no, let's make it x cubed plus x squared minus x, okay, minus 1 all over x squared plus 2x minus 3, where our limit is going to x is approaching 1. Okay, now if we do preliminary test, if we substitute 1 into this function, we will have 1 cubed plus 1 squared minus 1 minus 1 over 1 squared plus 2 times 1 is 2 minus 3. Okay, so you can see that the numerator will be 1 plus 1, which is 2, minus 2, which will be 0, over denominator will be 1 plus 2, which is 3, minus 3 is also 0. So we have an indeterminate form, right? Hence the need for us to re-express what this expression here. Okay, good. So how do we go about that? L'Hopital says we are just going to differentiate. So differentiating means we'll differentiate each of these terms here. So let's find the derivative. This is f of x, and then this is g of x. So it's of the form f of x and g of x. So we are going to find the derivative of the numerator. When we find the derivative, we bring the power down. That will be 3x. Then we subtract 1 from the numerator. That will be 2. Plus the next time you bring the power down, that will be 2. Then x, 2 minus 1, the power. You subtract 1 from the power, that will give us 1. Then minus, here the power is already 1. So when it multiplies, you get minus 1x raised to the power 0. Okay, and then the derivative of a constant is always 0. So it will be plus 0. Then now let's go to the denominator. We'll differentiate the denominator too. That will give us 2x. Then you subtract 1 from the power. It will be left with 1. Plus, there we already have 1. So it will be when 1 comes and multiply the 2, you get 2. Then x raised to the power of 0. Plus the constant is 0. Okay. So somebody will ask, say, why not minus 0 or minus 0 in the denominator? 0 is 0. Plus 0 or minus 0 doesn't matter. Okay, so take note of that. So if that is the case, now that we are here, we want to investigate whether if we put 1 into the function, okay, let's re-express this in the simplest form. That will be 3x squared plus what? 2x. Any number raised to the power 0 is 1. So this is minus 1 all over 2x plus x raised to the power 0 is 1. So plus 2. Now, the question is, if we evaluate the limit, that is putting x equals to 1 into this expression, are we going to get an indeterminate form? Okay, let's try that and see. If we put 1 here, it will be 3 times 1, which is 3. If we put 1 here, we'll get 2 times 1, which is 2. Okay, so 3 plus 2 will give us 5, minus 1 will be 4. So numerator will not be indeterminate. The same way, when we put 1 in the denominator, 2 times 1 will be what? 2. Plus 2 will be 4. So we'll get 4 over 4. So once we evaluate the limit, we will not get what? An indeterminate form. So we would evaluate the limit at this point. But assuming at this point, when you put 1, you still get indeterminate form, then differentiate the two functions again. Okay, that is what the L'Hopital says. So keep differentiating till you get a form which will not give you indeterminate. So this time we are going to evaluate the limit lim at x approaches 1. This will be equal to, when we substitute, we get 3 times 1 squared, which is 3, plus 2 times 1, which is what? 2, minus 1 over 2 times 1, which is 2, plus 2. Okay, so let me bring the final answer somewhere here. To the top will be preferable. So that will give us, numerator will be 5 minus 1, which is 4 over 4. Okay, and then 4 over 4 is equals to what? 1. So the limit of the expression we have there is equal to 1 using the L'Hopital's principle. Any question? Yes, Isaac.
Sir,
Yes.
please, if a question is given like that, how will you know it is L'Hopital the rule?
How will you know what?
How will you know it is L'Hopital rule?
There's nothing like a question which is L'Hopital's rule. When you examine the question and it's giving you indeterminates, then L'Hopital is another option which can be used to simplify what? The expression.
Okay.
So we've already looked at one option by dividing through by the highest power of the denominator. So L'Hopital is another option.
Oh, okay. So it depends. Maybe I can choose to use this L'Hopital, and the other person too can choose to use other rules.
Exactly.
Is that what you're saying? Okay.
Yeah, that's
Okay.
what I'm saying.
Okay. Thank you.
Yes. Now the L'Hopital is more general in the sense that there are functions like the trig functions.
Okay.
For trig functions, when differentiating, when dealing with them, sometimes it's better to apply the L'Hopital's rule. But because we have not done differentiation of functions yet, we cannot look at those examples for now. We have to do differentiation, and then if we get an opportunity, maybe we'll come and look at one of those limit questions.
Okay, sir. Okay, sir.
Yeah, I have Ibrahim's hand up. Ibrahim.
Yes, sir.
Yes.
My question was answered because I was asking if, apart from the L'Hopital's rule, you can also use the difference of two squares.
Yeah.
In order to avoid the determinate down.
Okay.
So that was what I was about to ask.
Dealing with the limit of trig functions, sometimes the limits can be a bit tricky. Okay. So for example, there are standard limits like the limit of sine theta over theta will always give you, as theta approaches 0, will always give you a value of 1. It's a rule, you must know it. Then the limit of cos theta minus 1 over theta will always give you, as theta approaches 0, will always give you 0. This is also a rule you must know. Okay. So for example, if I give you a question like this, to find the limit of sine 6x over x, what the rule here is, or let me say the trick here is, you always want to re-express what is in bracket here and the denominator to be the same. They always have to be the same, because the rule says theta sine theta over theta will always be equal to 1. So if you can express the value in the denominator to be equal to the value in the bracket here, then you just apply the rule and then you get 1. So let's see how this works. So this will be, now I have sine 6x over here, and the denominator is only x here. Okay, as it stands now, this is 6x, this is x, so they are not the same. But if I multiply the numerator by 6 and divide by 6, then I can re-express the denominator as what? 6x. So this will look like this, sine sine 6x, okay, over 6x. You see, so now this is looking like sine theta over theta because we have 6x here, which is theta, and then 6x here, which is also theta. Okay, so if that is the case, when I find the limits of that resulting expression, which is sine 6x over 6x, this will give me per the rule, a constant times a function will be just a 6 limit of sine 6x, okay, divided by 6x. And then per this rule here, sine of a theta divided by theta. When we find the limit as x approaches 0, will always be equal to what? 1. So as x approaches 0, sine of 6x over 6s will be equal to 1. So this will be 6 times this whole thing per the rule says this whole thing is going to be equal to what? 1. Okay, so this is going to be 1. And the limit is equal to what? 6. It's quite an interesting expression here. Okay. Any questions? Now, I'm going to try the next problem too. So I'm going to take the next, I'm going to take this, which is the last example there, using the second rule here, okay? It's quite similar to the first. So in this case, when I want the limit, I have cos, okay, 2z in brackets. So theta is 2z here, right? Minus 1. And the denominator is only z, it is not 2z. So if I want it in this form, then I have to make the denominator 2z. And the only way to make the denominator 2z is to multiply by 2 and then multiply the top 2 by 2. So this 2, when these 2 cancel out the 2, it will be 1. Means you have not changed the expression. Good. So if that is the case, then this form is looking like what we have up here. So we can now evaluate the limits. So when we find the limit, it's going to be equal to 2 limits of what? Cos of 2z, okay, minus 1, all over 2z. So per the principle at hand, so per our principle there, the whole of this is going to be equal to what? Is going to be equal to what? 0. So this means that we are going to get 2 times what? 0, which means that the limits of cos of 2z minus 1 over 2z is equal to 0. Okay, so I'll take the final questions on that whilst we wrap up on today's class regarding limits. So if you have any question, you can raise your hand up. Yes, Kadil Ibrahim. Kadil Ibrahim.
Yes, sir.
Yes.
Please, for this kind of example that we do understand, we want you to go through with the example D
Okay.
so that you have more understanding.
Okay, that's fine. Once you understand, we don't have a problem. New Timothy.
Hello, sir.
Yes, Timothy.
Please, I'm a little bit having a poor connection here, so I didn't get the whole thing.
Okay, so video will be made available after class. Okay, so let me repeat that. So for this third example, we can write it as 3 sine t. Okay, sine t, 3t divided by sine 8t. And like I explained, just to express it in this form, in the form of the rule, divide through by 3t and multiply by 3t. Then for the other term, to divide by 80 and multiply by 80. Okay, so then we are going to get 3t sine 3t over all over what? 3t. Okay, then I'm going to change the division to the inverse of it. So this will give me 8t over what? 8t sine of sine of what? 8t. I'm even thinking I want it in a much simpler, very simple form, okay, for us to observe. This looks like this form already. So maybe we have to keep it in that form. And yes, let's keep it in that form. So instead of going this process, I'll prefer we just evaluate limits, okay, from this point of view. So this is going to give me, when I find the limits, so limit is going to give me limit of what? 3t times the limits of, just a minute. Let me go back. There's something we have to delete. I wanted us to write it in a much simpler form, but it looks like we have no option. This will give us 3t sine of 3t over 3t times. So when we change the division, now is going to be the reverse. So that will be times 8t over 80 sine of what? Sine of 8t. Okay, good. So this is the expansion we are looking at. Just that it's in the inverse, and now it is theta over sine theta. Okay, and then this one too is this over that. Right? Good. So if we look at it carefully, this is how it will look like. It is now 3t over what? Over 8t times, I'm multiplying everything. So that will be times sine of what? 3t, okay, over 3t times what? This will be 8t over sine of what? 8t. So this is much clearer to you, right? However, don't forget, this is now sine theta. This is now theta over sine theta. You just have to find the inverse of it. This is sine 3t, this is sine theta over theta. But this t will cancel out this t. So you have a constant there. Okay. So you're going to find the limit. I've given you the clue to this point. So you at home, you are going to solve question C and then question D for B, given the level to which we have solved. Just complete it for me at home and I will take it in class when we meet physically. Okay. So I can see somebody's hand is up. Okay. So if there is no further question,